Hi everyone, so welcome to week 9. Week 9 is going to have us finish up chapter 11, which focuses on area, and we're actually going to start our last chapter of the year, chapter 12. So first we're going to finish off chapter 11 with 11.7, which focuses on ratio of areas. And we're going to talk about how we can compare areas of similar figures and non-similar figures. So in terms of similar figures, we know that similar figures, specifically similar triangles, their angle measures are all the same, but their sides are proportional to each other. And we know that the ratio of any pair of their corresponding altitudes, medians, or angle bisectors are equal to the ratio of the corresponding sides. So now we're going to say if two figures are similar, to find the ratio of their areas, so the first shape to the second shape, we can take their two side lengths, put them over each other, and square it, and that will be the ratio of the areas. And this comes in handy when we only know one side of our triangle. So if you see in my example here, all I know is that this side is 4 and this side is 6. I don't know the base, I don't know the height, so I should be able to use this theorem, but we're going to see if we can prove it. So here we could see that the ratio of the sides, they're in a 6:4 ratio, or we can simplify that to 3/2. And in theory, if we were to square this, then that should equal the ratio of the areas of the two triangles. So we're going to see if we can prove it. So if we were to write this out, we know that in order to find the area of a triangle, it's 1/2 base times height. So we're going to say that this is our base and that's our height of the bigger triangle, and base and height of the smaller triangle. Now what ends up happening here is the 1/2s cancel each other out, and we're left with the bases and the heights. But like I said before, if we know the ratio of the sides, then the corresponding sides, the corresponding altitudes or heights are also in that same ratio. So for instance, base 1 over base 2 will also be in this 3:2 ratio, and height 1 to height 2 will have to also be in this 3:2 ratio. So what ends up happening here is we've got 3/2 times 3/2, because I'm just substituting 3/2 in for my two fractions. And what does that equal? That equals 9/4. And we said if we take this 3/2 and square it, it should equal the ratio of our areas. And again, we get 9/4 because we're doubling it. So this is proof to show that for similar figures, if we square the side lengths, then we should be able to find the ratio of their areas. The other theorem that is focused on in this section has to do with the median of a triangle. So we know a median of a triangle. So for instance, if AM is the median in this triangle, it comes down and it divides the base into two equal pieces. So these two would be the same length. Let's say Y and Y. Now, this theory in our textbook says that not only does this median divide the base into two equal pieces, but it divides these two regions, these two triangles, into two equal areas. So we're going to see if we can prove that right now. So I'm going to actually draw in my altitude or my height, and I'm going to label that X. So we want to see if we can figure out what the ratio of the area of triangle ABM to the area of triangle ACM is. So we're going to use this X and this Y to help us out. So triangle ABM. Triangle ABM is an obtuse triangle with a base of Y and a height of X. So if I was going to do that triangle, it would be 1/2 base times height. And for the second triangle, ACM, again, the height is X and the base is Y, so it's 1/2 base times height. The 1/2s cancel, so we're left with YX is to YX, which is really just equal to 1. So you can see that the areas here are in a 1-to-1 ratio. And that's because the triangles have equal bases and equal heights, so therefore their areas are going to be equal to each other. So these are our different ways of figuring out the ratios of areas. We could just calculate area over area. if there's similar figures, we could do side over side squared. And if there's a median, we know that it's going to divide this into two equal areas. So now let's do some practice problems. So for number 1, find the ratio of the area of the parallelogram to the area of the triangle. So as you can see, these are not similar figures. They're not even the same shape. So we actually have to find the area of each in order to figure out what the ratio of their areas is. So for the parallelogram, it's base times height, which is where the 90 came from. And the triangle, it's 1/2 base times height, which is where the 48 came from. So now, to find the ratio of the area of the parallelogram to the ratio of the triangle, I can create a fraction. I can say 9 over 48. And in my calculator, I can actually simplify that. So if you put 9 over 48 and then you press second table, it actually changes it to a simplified fraction for you. So 15 over 8. And you can leave your answer as a fraction, or I like to actually write it just like this, 15 to 8. So that is the ratio of the areas of the two figures. So for the second one, given the similar pentagons shown, find the ratios of their areas. So I'm not going to sit here and I'm not going to find the area of each pentagon because I can't. So I am going to use my S1 over S2 squared. So side 1 to side 2, we've got 12 to 9, and that is going to simplify to 4/3. And now I'm going to take that 4/3 and I'm going to square it in order to get the ratio of the areas. So you get 16 is to 9. Or you can write your answer just like this. And that is the ratio of the areas of the two pentagons. So let's look at number 3. If triangle ABC is similar to triangle DEF, find the ratio of the areas of the two triangles. So just like the pentagons, I have to take the ratio of the sides and square it. So 12 to 8, and they wrote the ABC first, so that's why I put the 12 on the top. And that is going to simplify to 3 over 2. And then if you square that, we are going to get the ratio of our areas, which is 9 over 4, or 9 to 4. Now, if the ratio of the areas of two similar parallelograms is 49 to 121, find the ratio of their bases. So this time they're giving you the ratio of the areas already. So since this is the ratio of the areas, I need to work backwards in order to figure out what the two bases are. So normally we would square the two bases, so I'm going to do the opposite. I'm going to square root these two numbers. So what ends up happening is I end up figuring out the square root of 49 is 7. The square root of 121 is 11. So that is the ratio of the area of the bases, 7 to 11. Doesn't get that much harder than this. So last problem. In the diagram, AB is 5 and BC is 2. Find the ratio of the area of triangle ABD to that of CBD. So for triangle ABD, the base is 5, and I drew in my height to label it h. So the area of this triangle would be 1/2 5 times h. For triangle CBD, since it's obtuse, this piece out here, this h, is also the height of triangle CBD. So here you would have 1/2 2 times h. So what ends up happening is the 1/2 end up canceling out, and the h's end up canceling out. So you could see that the ratio of the areas of the two triangles is just 5 over 2, or 5 to 2. So be careful. So this was not a median problem. This was different because the two bases are different. So by writing out the areas and canceling out the variables, you're able to see what the ratio of the two areas is. And that is the end of chapter 11.